Hello, this is John Garfula with Module 2, Teach the Doc number 2, where we're going to be going over the structure of atoms, as well as identifying what quantity and components make up compounds as well as elements. So just going to start right off the top. Give the atomic number for each of the following elements using the periodic table as reference. So we have a periodic table in our notes. So this is going to be pretty easy. Just match up the element with the atomic number. So C which is carbon, right here, atomic number 6. Just plug that in, number 6 right there. Fe is iron, located right here. So that's atomic number 26. Plug that in. And then Br is bromine, which is right over here, atomic number 35. Pretty simple stuff there. Moving on, mass number is equal to the number of blank and blank. Its mass is equal to the number of protons and neutrons. I threw in a little reference right here to show some quick conversions and how to identify other data about an element given a limited set of information about it. So for the first problem, we're given, I should say for the first 2 lines, we're given the element as well as some data about it. So for the first, we're given a mass number 35 with an atomic number 17 and the element, which is chlorine. So we need to go through and figure out what the rest of this information will be. Well, we know that the mass number is 35 based on the information provided. And we know that there are 17 protons based on the information provided. So then to identify how many neutrons we have, we'll just take 35 minus 17, which gives us 18. There's no charge indicated, so we know that the number of electrons is equal to the number of protons. So we have 17 and 17 there. And we know that the number of protons is equal to the atomic number, so we can fill in 17 there as well, and 0 for no charge. In the following line down, we've got zinc with an atomic mass of 64, an atomic number of 30, and indicating a +2 charge. So we can go ahead and start filling some of this out right now. We know the atomic number is 30 right off the bat, and that means that we're going to have 30 protons as well. We know that the mass number is 64, so we can plug that in right there. To get to our neutrons, we take the atomic number or protons, whichever one you want to use, and subtract it from the mass number. It gives us 34 neutrons. Now, how do we find the electrons? Well, what we do is we look at the charge, and since it's +2, we know that it's a positive charge of 2. So we subtract 2 to get to the total number of electrons, which is 28 there, and then just plug in the charge. Pretty self-explanatory there. The next one's a little bit more difficult. We're given the number of neutrons, the mass number, and the charge, and we've got to figure it out from there. So what we can try to do is figure out the atomic number first. We'll take the mass number, subtract the neutrons, which gives us 31. So we're looking for the atomic number 31. And so we can reference that over here, which we've got gallium is number 31. So we know we're dealing with gallium, and we know that we've got 31 protons. Knowing that we've got a +3 charge, we subtract 3 from the number of protons to get to our electrons. There's 28. So the resultant would be, if I were to write this out in a similar structure as the professor did in the first 2 lines, it would be 65 over 31 Ga with 3 plus. We go to the next one. We are given the protons, the neutrons, the electrons, and the mass number. So we've got a good chunk of information to figure this out. So we know that the atomic number is equal to the protons. So we look for number 34, which is selenium. So we know the element. And then we also know what the charge is because we can compare the protons to the electrons. Since we have more electrons, we're going to have a negative charge here, a factor of 2. Not a factor, but a total of 2. So we know that our charge is -2, and we know that our atomic number is equal to the number of protons, which is 34. And that gives us, again, if I were to reformat this, it would be 79 over 34 Se2 minus. Moving on down, practice problem, calculate the atomic mass for lithium given the following information. And I threw that in as reference for the conversion, or the calculation factor. So we're given 2 mass and abundance figures here for lithium. The calculation to convert these to identify the atomic mass for lithium is to take the mass times the abundance plus the mass times the abundance of another value. Since we have 2 values here, we'll go ahead and plug the data in as such. And just a quick note about significant figures here. The smallest number of significant figures we have is 4. So my resulting answers have 4 significant figures in it as well. And calculating out the arithmetic, we come up with a value of 6.940 AMU. Next, we're going to be talking about ionic compounds. And so watching the videos on this on YouTube really helped kind of formulate how these are named and written out. So just the example, the 10 examples I came up with, sodium chloride, sodium fluoride, again, all of these are going to end in IDE, and they're all ionic compounds. So calcium iodide, cobalt chloride, copper nitride, lithium chloride, potassium bromide, iron oxide, sodium hydroxide, mercury oxide. And so how do I identify which ones are going to have multiple instances of a given element? Well, the material online gave an example of which columns had plus charges. And so in order to make the equation, or in order to make the charge 0, that's how we come up with the total number of elements involved. The next topic is going to be covalent compounds, working with binary molecular compounds. And this was an interesting one in order to write out the long form version of the element using prefixes to identify how much of a given element is in a particular compound. So the 10 compounds I came up with were sulfur hexafluoride, which is SF6, and hexa meaning 6, and then dinitrogen pentoxide, again, di meaning 2 and pent meaning 5. And again, in the video, it's very descriptive about how we can drop vowels that would be confusing when we're trying to pronounce some of these things. So dinitrogen trioxide, N2O3, tetraphosphorus decosulfide, which is obviously 4 phosphorus and 10 sulfides. Carbon tetrafluoride just combines CF4, phosphorus pentachloride, PCl5, dichlorine heptoxide, Cl2O7, tetraphosphorus hexoxide, P4O6, carbon monoxide, obviously pretty simple there, hydrogen chloride, HCl. And then getting into the acids, again, it was helpful to have the naming convention hydro plus the name of the non-metal, and then inserting IC at the end of it, plus acid. So that really helped come up with the answers for this particular question. So again, all of these will begin with hydro, insert the core of an element, and then IC plus acid. So I've got hydrobromic acid, hydrofluoric acid, hydroselenic acid, hydrophosphoric acid, hydronitric acid, hydrosulfuric acid, hydrochloric acid, hydroiodic acid, hydrocyanic acid, and hydroxic acid, or H2O. I thought that was interesting, that water could be considered an acid. Then we're looking at oxyacids, which are all going to be, they'll all have oxygen in them in some factor. And then it goes through how to name that particular acid. So they all have a hydrogen base, and then an additional element or elements afterward. So nitric acid, HNO3, carbonic acid, H2CO3, acetic acid, HC2H3O2. That's kind of one of the more complex ones that I came across. Sulfuric acid, H2SO4, phosphoric acid, H3PO4. And finally, we're talking about oxyanions, ending in OUS. 5 examples here. And these, again, most of these came from the video, but chlorous acid, HClO2, chromous acid, HCrO2, nitrous acid, HNO2, phosphorus acid, H3PO3, and sulfurous acid, H2SO3.